G'day, in this video we're going to dig a little deeper into transformers, look at how they are applied in everyday life, as well as some limitations that we have with the model. So today we're going to be covering the last two dot points of inquiry question 3, dot points 4 and 5. Dot point 4 focuses on how the ideal transformer is a limited model. There's actually some things that are happening in real life for a real transformer, which means that the quantitative relationships that we've talked about previous don't exactly hold up. And dot point number 5 gets us to look at the application of both step up and step down transformers. So transformers which increase and decrease voltage respectively. So our key aims, I'm going to look at applying transformers first. So we'll explain how step up and step down transformers actually work, unpack how these transformers are applied to the distribution of electrical energy, as well as some other applications. And then what we'll start to do is look at how the ideal transformer model and our equations that we unpacked last lesson aren't exactly reflective of what happens in real life. And once we understand why the ideal transformer model isn't perfect and why there are some limitations, we're going to look at ways in which we can make transformers behave and act more efficiently. So first off, let's look at step up and step down transformers. So we've got a step up transformer on the left and a step down transformer on the right. We can see here that the primary coil has less loops than there is in the secondary coil for step up, and vice versa. Primary coil has more loops compared to secondary for step down. To show what implications this has for the primary and secondary voltage and current, I'm going to be reflecting back on this key equation that we derived together in the last video. So for a step up transformer, we know that the number of coils in the secondary is larger than the number of loops which is in the primary coil. Reflecting on our equation where Vp on Vs is equal to Np on Ns, what that means is an increase in the number of coils in the secondary is going to also increase the voltage in the secondary. What that means is that Vs is always going to be greater than Vp. However, this is not the case for current. If we increase voltage, then we should expect that current should be decreased, and that is reflected in the equation. Therefore, we can say that Is is actually going to be less than Ip. So for a step-up transformer, what we need to do is increase the number of loops in the secondary coil. This will increase the voltage in the secondary coil, but decrease the current. Step-down transformers have the same pattern, but work in the opposite way. In this case, by decreasing the number of loops in the secondary coil, we will end up decreasing or stepping down the voltage in the secondary circuit. And on the flip side, we'll be increasing the current that's in the secondary coil. Now, depending on the situation and scenario, there could be appropriate times to step up or appropriate times to step down. When we look at electricity transmission, we need scenarios where both things are happening. At a power station, we generate electricity, and when we use our high voltage transmission lines, which carry electrical energy over extremely large distances, we use step-up transformers to increase voltage and decrease current. If you take a closer read of the paragraphs that are over here, what's said is that large amounts of current will cause, and this energy loss will occur as flowing electrons collide with matter that is in the conductor itself. Those collisions generate heat, and energy thus is lost. What you end up with is a reduction in power by the time it gets to the home. If there's a reduction in power, you've lost energy. There's a drop in overall voltage and current by the end. However, if we do step up at the power station before we get to the transmission lines, you'll have a high voltage and a low current, which is able to move electrical energy long distances without there being large energy losses. Once you then get closer to the home, you'll end up seeing a series of step-down transformers. These transformers are periodically converting high voltage energy to lower voltage energy with a larger current. At this stage, because the energy has a smaller distance to travel, those efficiency concerns are not as great. What becomes a concern is as we bring some of these electrical lines closer and closer to people in residential areas and the like, we start encountering issues of safety. We don't want people to be in close contact with power lines of extremely high voltage, which can cause injury or death. And through these series of transformers, we step our electrical energy down and down until we get to our home grade voltage. For Australia, this is 230 volts. So as just explained before, you will see transformers on all sorts of power lines and different stages in our transmission grid, which will again allow for safe transmission of electrical energy in local areas where the energy is moving over low distances. Beyond that, when we get our 230 volts coming out of our power points, that's not necessarily going to be compatible with many of our electrical appliances. So what you will end up with are transformers which are either attached to or a part of the socket, which are able to transform the energy and step it down even further, so that there is an appropriate voltage running through the circuits of that particular electrical device. As we've hinted at already, the ideal transformer is clearly not ideal in real life. There are lots of different assumptions that we are working with to assume that there is 100% efficiency within the transformer, 100% efficiency in transferring electrical energy from the original primary coil to the secondary coil. The first thing that I want to talk about today is flux linkage. That essentially is the flux which is able to pass from the primary coil to the secondary coil, the connection between the primary and secondary coil through flux rather than an electrical current. So this is the flux that is moving around our ferromagnetic core. In an ideal transformer, we assume that there is 100% linkage. In other words, all of the magnetic field which is being generated by the primary coil is able to transfer completely over to the side where the secondary coil is. In actuality, this is not completely the case. What will happen is that some of the flux will leave the core, and we call this flux leakage. What that leads to is eddy currents being generated in surrounding materials. And as that flux leaks, we end up getting an energy conversion from that original electrical energy from the primary coil, which ends up turning into heat and or sound energy. Another thing that happens is resistive heat. Essentially, if you have a current or electrons flowing through a wire, there will be collisions between atoms or electrons attached to atoms within the conductor. These collisions will lead to the generation of heat. That generation of heat is an energy loss, and that energy loss will mean that you won't get 100% of the energy that was coming from that primary coil ending up in the secondary coil. Another thing to add to this is the idea that hot objects have higher resistance. So if you start generating heat, that's going to mean that the conductor particles are going to vibrate more. So in your wires, you're going to have more vibration in those conductors. If they're vibrating all over the place, it's more likely that more electrons will collide. What that means is you end up with more resistance because of more of those collisions, which only means that there's more energy loss. So being able to manage the heat generation in a transformer, as well as other electrical components, can be really important to ensure that you are getting efficient transfer of energy. So obviously in an ideal transformer, we're going to assume that no resistive heat occurs, meaning that the power that is going into the core is the same as the power going out of the core. Not entirely the case, but an assumption that we run with nonetheless. In a real transformer, there is resistance in the wires. That resistance is causing energy loss, and that will mean that transformers will heat up through the process and increase resistance unless there is a strategy to maintain temperature. In a similar way, but slightly different, we also have heat being generated by eddy currents. So particularly we're looking at eddy currents which are within the transformer, not eddy currents generated near or on the outer parts, the shell of the transformer itself, but rather we're looking here at the ferromagnetic core. So by Lenz's law, the ferromagnetic core will produce an opposing magnetic flux and thus generate eddy current. So if you've got flux moving through that ferromagnetic core and the flux is changing, you're going to end up getting essentially a back EMF, some sort of electromotive force, which is in the form of an eddy current, which will generate opposing magnetic flux. If you have eddy currents, we know that that means that you've got these free electrons, this current moving through the conductive object. That's going to cause collisions with atoms, just as we talked about in the previous slide, and that's going to lead to the production of heat as well. If there's production of heat and electrons moving through eddy currents when they're not supposed to be, obviously this is also energy loss. So for an ideal transformer, we generally assume that there's no eddy currents, but in the real world, there are eddy currents and they produce heat, just like shown in this picture where we can see that the transformer is much warmer than its surroundings. That production of heat will lead to an energy loss. So how do you make ideal transformers more efficient? One way to do it is laminated iron cores, where there are insulators in between smaller sheets of ferromagnetic material. What this allows for is for the transfer of flux while reducing the amount of heat loss through eddy currents. By giving the electrons smaller space to work in, you end up reducing those eddy currents, reducing heat produced. And they're also designed in a way where heat is more readily able to escape from each of those layers as well. Another way that we can make transformers more efficient is by using ferrites, which is a slightly different material that could be used to make a transformer's core. Essentially, these ferrites are non-metal materials. They're oxides, some sort of iron oxide generally. They have high transmission of magnetic fields, but low electrical conductivity. They don't behave like an iron core would. What this means is that you will end up reducing eddy currents in the core and thus reducing heat production. Thank you very much, everyone. In the next video, we're going to start to look at applying everything that we've learned so far to the real world. We're going to be looking at how motors are created, how the motor effect is taken advantage of to create many different appliances that are very effective and helpful for us in our everyday lives. Until then, have a good one.